Welcome, everyone. I'm excited to take you through the fascinating world of satellite technology from a broadcast engineering perspective. Satellites have completely transformed how we communicate globally, enabling everything from television broadcasts to internet connectivity across vast distances. Today, we'll explore how these remarkable pieces of technology actually work, examining their design, function, and the intricate systems that make global broadcasting possible. Let's start with the basics. What exactly is a satellite? In simple terms, satellites are artificial objects placed into orbit around Earth. These sophisticated machines serve as the backbone of our global communication infrastructure. Since the launch of Sputnik in 1957, satellites have evolved into diverse platforms serving multiple functions, from broadcasting television signals to enabling GPS navigation and Earth observation. Today, there are thousands of satellites orbiting our planet, forming an invisible network that connects the world. The evolution of satellite technology has been remarkable. In 1962, Telstar made history as the first active communication satellite, capable of receiving and retransmitting signals rather than just passively reflecting them. By 1965, Intelsat-I, nicknamed Early Bird, revolutionized the industry as the first commercial geostationary satellite, meaning it remained fixed above a single point on Earth. The 1970s saw the rise of regional broadcast satellites like Marissa and Palapa, expanding television access across continents. A major shift occurred in 1994 with DirecTV, which popularized digital broadcasting directly to homes. From 2009 onward, we've seen remarkable advancements in broadcast quality, moving from HD to 4K and now Ultra HD capacity, dramatically increasing the amount of data satellites can handle. For broadcast engineers, understanding orbital mechanics is crucial. Geostationary orbit, or GEO, sits at precisely 35,786 kilometers above Earth's equator. This specific altitude is critical because it allows satellites to orbit at exactly the same rate the Earth rotates. From our perspective on the ground, these satellites appear completely stationary in the sky, a perfect position for consistent broadcasting. These orbital slots are valuable real estate, typically spaced about 2 degrees apart to prevent signal interference. Each satellite completes one orbit in 23 hours, 56 minutes, and 4 seconds, matching Earth's rotation perfectly. This special orbital characteristic is what makes satellite broadcasting possible on a global scale. Getting a satellite into its proper orbit is an incredible feat of engineering. The process begins with launch, where a rocket delivers a satellite to what's called a transfer orbit. Once in space, the satellite undergoes a carefully orchestrated deployment sequence. Solar panels unfold to capture energy, and complex antenna systems extend to their full size. Next comes a rigorous testing phase, where every system is verified before the satellite becomes operational. The final positioning phase takes between 1 and 2 weeks, as thrusters carefully maneuver the satellite into its precise orbital slot. It's a delicate dance requiring precise calculations and adjustments to reach the exact position needed for optimal broadcasting coverage. Modern broadcast satellites are marvels of engineering. At their core are transponders, typically 24 to 72 individual units that receive, amplify, and retransmit signals. These are powered by sophisticated systems generating between 5 to 15 kilowatts through solar arrays. The steerable antennas are particularly impressive, allowing precise targeting of signals to specific geographic regions. Propulsion systems maintain the satellite's attitude and position, performing regular adjustments to keep it perfectly aligned. Perhaps most challenging is thermal management. In the vacuum of space, temperatures can fluctuate between extreme heat and cold, requiring sophisticated systems to maintain optimal operating temperatures for sensitive electronics. The basic principle of satellite broadcasting follows a 3-stage process. First is the uplink, where ground stations transmit signals up to the satellite. These transmissions contain everything from television programming to internet data. Once received by the satellite, the signal undergoes processing. It's amplified, potentially converted to different frequencies, and prepared for redistribution. Finally, during the downlink phase, these signals are broadcast back to Earth, where they're captured by receiving dishes, from large professional arrays to the small dishes you might see on homes. This entire process happens at the speed of light, with signals traveling the vast distance between Earth and orbit in just fractions of a second. Looking ahead, satellite technology is poised for remarkable advancements. Quantum communication represents perhaps the most exciting frontier, promising virtually unhackable transmission security through the principles of quantum physics. We're also seeing the rise of mega-constellation networks composed of thousands of smaller satellites working in coordination. Higher bandwidth capabilities will support 8K resolution and beyond, providing increasingly lifelike viewing experiences. And as space becomes more crowded, sustainable design practices are becoming essential, with new satellites specifically engineered to minimize space debris at the end of their operational life. The technical details of satellite transmission frequencies are crucial for broadcast engineers. For uplink transmissions, we typically use C-band frequencies between 5.9 and 6.4 GHz, or Ku-band between 14 and 14.5 GHz. Each band has specific advantages. C-band is less susceptible to rain fade but requires larger dishes, while Ku-band allows for smaller receiving equipment but can be affected by severe weather. For downlink, C-band operates between 3.7 and 4.2 GHz, while Ku-band uses 11.7 to 12.2 GHz. Understanding these frequency allocations is essential for properly configuring both transmission and receiving equipment throughout the broadcast chain. With limited orbital slots and frequency spectrum, efficiency is paramount in satellite broadcasting. Several techniques maximize these resources. Frequency reuse allows the same frequencies to be used multiple times by separating them through different polarizations. Speaking of polarization, signals can be transmitted using horizontal/vertical or right/left circular polarization, effectively doubling capacity. Spot beam technology enables precise targeting of signals to specific geographic areas rather than broadcasting across an entire hemisphere. Finally, bandwidth optimization techniques compress and configure signals to transmit more information using less spectrum, critical as demand for satellite services continues to grow. Modern satellite broadcasting relies on sophisticated signal processing. Video compression standards like H.264/AVC and H.265/HEVC dramatically reduce the bandwidth needed for high-quality video transmission. Transport stream technology efficiently packages multiple channels together, allowing hundreds of services to share limited satellite capacity. Conditional access systems ensure secure content delivery, preventing unauthorized viewing of premium content. Additionally, advanced error correction techniques like forward error correction (FEC) and variable coding maintain signal integrity even under challenging conditions, ensuring viewers receive clear, uninterrupted service regardless of minor transmission issues. On the reception side, several key components work together. Dish sizes typically range from 45 to 90 centimeters for home reception, with the exact size depending on local signal strength and frequency band. The low noise block down converter, LNB, is crucial, with modern units achieving noise figures below 0.7 dB for exceptional signal clarity. These LNBs convert the high-frequency satellite signals down to L-band, 950 to 2150 MHz, for distribution through standard coaxial cables. Today's receivers incorporate advanced decoding capabilities, supporting multiple video standards, interactive services, and internet connectivity, transforming what was once simple television reception into a comprehensive entertainment platform. The satellite industry continues to evolve rapidly. High-throughput satellites have revolutionized capacity, delivering exponentially more data than traditional designs. We're seeing a shift toward IP-based transmission, integrating satellite delivery with internet protocols for seamless connectivity. Software-defined payloads represent another major advancement, allowing satellites to be reconfigured while in orbit to adapt to changing market demands. Perhaps most revolutionary are the low Earth orbit (LEO) mega-constellations being deployed, which orbit much closer to Earth than traditional broadcast satellites, providing lower latency and potentially reshaping how broadcast content is distributed globally. The future of broadcasting isn't about satellites alone, it's about integration. Modern networks increasingly combine satellite transmission's wide area coverage with other technologies. Hybrid integration enables seamless convergence between satellite, fiber, and wireless delivery methods. The rollout of 5G networks complements satellite systems by providing high-speed local distribution where terrestrial infrastructure is available. On the consumer side, end-user devices are increasingly designed with multi-source reception capability, automatically selecting the optimal delivery method based on available networks. This convergence creates a more resilient, efficient content delivery ecosystem than any single technology could provide alone. As we look to the future of broadcast engineering in space, several key principles will guide development. The industry's commitment to 99.99% reliability remains unwavering. That's less than 1 hour of downtime per year, reflecting the mission-critical nature of broadcast infrastructure. Satellites will continue to serve as the backbone of global content distribution, reaching areas where terrestrial infrastructure is impractical. RF engineering will remain fundamental, with increasingly precise orbital mechanics enabling more efficient use of limited resources. Throughout all this, standard will continue to evolve, maintaining backward compatibility while embracing new technologies. The future of broadcast engineering in space is bright, built on decades of innovation and poised for even greater advancements in the years to come. Thank you for joining me on this exploration of satellite technology from a broadcast engineering perspective. I hope you've gained a deeper appreciation for these remarkable systems that connect our world.